In this section, we're going to talk about systems of particles. So let's begin by developing an expression of Newton's second law for a system or group of particles. So suppose we have n particles, some arbitrary number, and call each of them p sub I, where I is 1, 2, 3, so on up to capital N. Each particle has a mass m sub I, an acceleration a sub I. Now each of these particles, so here I've drawn a picture with a few particles, 1, particle 2, and here's particle I and j, two arbitrary particles in the system. Particle I has a net external force of capital F sub I. And also acting on particle I is an internal force due to particle j, and there will be one of these potentially for each particle, and it's called little f sub I j. So that's the internal force. This is the internal force by the jth particle on I. So we can write Newton's second law for the ith particle, and it will look like the following: the net external force plus the sum of all internal forces, so in this case we're summing over j, equals the mass of the ith particle times its acceleration. We can also take the moment of this equation about the origin, like that. Now, if we recognize the fact that for every internal force F sub I j, that is the force on I by j, there will be an equal and opposite internal force F sub j I. That's the force on the jth particle by the rth particle. Those will all be equal and opposite. So if we start looking at Newton's second law for the system, those internal forces will cancel. And also all of the moments of the internal forces will cancel. Now, we can look at writing the sum of all Newton's second laws for the system. We can add all of these together for each particle. We can also add all of the moments together for each particle. And we'll notice that the internal forces and their moments will cancel out. And if we do that, we'll come up with a set of equations for the system that looks like the following. So this is a set of equations, two equations for the entire system. This one says that the sum of all forces acting on the system equals the sum of all its masses times accelerations, and similarly for the moments. Just like we've done in the past, we can define the linear momentum for the system as the sum of all the linear momentums of each of the particles in the system. We can also define the angular momentum for the system as the moment of the momentum for each particle in a system. And whenever you take the angular momentum, there's an implicit origin in that. So this is the origin that we have called O. And so with that in mind, we can write our equations of motion for the system as the sum of all external forces equals the time rate of change of the linear momentum, and the sum of all moments about the origin equals the time rate of change about O of the angular momentum. So here we have a set of equations. We have two equations expressing the momentum and angular momentum as they relate to forces and moments. And this is for a system of particles. Now we can write Newton's second law for a system of particles in another form, and that is with respect to the system of particles mass center. Okay? And so we can define this mass center with the following equation. So r hat, this is the position of the mass center for the system of particles, also called the center of gravity. And the r sub I is the position of each mass m sub I, and this m is the total system mass, so the sum of all m sub i's. And so usually what we're trying to do is find this mass center, and we find it through this definition. Okay? Now, if we use this definition for the mass center, we can write our two equations of motion in a new way. That is, by noting that the linear momentum for the system is equal to the mass, capital M, total mass of the system times v hat, the velocity of that mass center, which is m times r hat dot. Okay, so this is the velocity of the mass center for the system. And this is the total mass of the system. Right, and this is the linear momentum of the system. Now we had just written a moment ago the definition of linear momentum of the system. This is also equal to the sum over all particles m sub I v sub I. So this is the definition of the linear momentum of the system. This is another way of expressing it. And so with that definition we can write Newton's second law. So the sum for the system, the sum of all forces, external forces acting on the system of particles, equals the total mass of the particles in the system times the mass center's acceleration. So what this equation says is that the equation of motion says is that we can write our equation of motion for several particles, as we did before, or we can write our equation of motion as if all external forces are acting on the mass center. Okay? And then we look at the motion of that mass center, right? This is the acceleration of that mass center, as a single unit, as a single particle. Okay? But keeping in mind, though, that we have several different particles involved in the motion. Now we can talk about angular momentum of a system. When we begin to talk about systems and particles, and as this leads into rigid bodies, the angular momentum becomes a much more important concept. It's not as important to describing the kinetics of individual particles, But for systems of particles, angular momentum becomes important. So what we want to do is we want to write now the angular momentum we want to come up with an expression for the angular momentum, not about an arbitrary coordinate system, but about a reference frame, a coordinate system at the mass center. Suppose we have a system of particles, and maybe our particles are located like this arbitrarily in space, but they have a mass center that's located here. I want to develop a new coordinate system that's attached to the mass center, okay, but whose orientation does not change with respect to the mass center that we'll call, or excuse me, the coordinate for reference frame we'll call O. So its orientation, the axes all remain parallel as the mass center moves around, no rotation, but it's centered on the mass center. In this case, I can say that the sum of moments about G is equal to the time rate of change of the angular momentum about G. That's just the moment of Newton's second law that we mentioned a second ago, but with respect to reference frame G. I haven't changed it. This is nothing new. I can furthermore express this angular momentum time rate of change just from the definition as the sum of the positions of all particles cross with m sub I, a sub I. Now, the important thing is I'm doing this with respect to G, so I'm going to put a prime on that r sub I. This indicates that that position vector is written with respect to this new reference frame. So with respect to G, the mass center. And so I'll also put a prime on that just to indicate that we are taking this moment with respect to the reference frame attached to the mass center. Now you can show the following equivalency. You can show that the angular momentum, time rate of change of the angular momentum with respect to G taken with regard to this new reference frame is exactly the same as the time rate of change of the angular momentum taken with respect to the absolute reference frame. This is a really subtle difference. Let me expand these with using their definitions. Okay, so the angular momentum with respect to G is equal to the sum of all r sub i's primes, right? So I'm taking the moment with respect to G cross with the momentum. In this case, the momentum is in the absolute frame, okay? And this is equal to the moment taken with respect to G, okay, so that hasn't changed, cross with the linear momentum of each particle in the reference frame attached to G. So that's the subtle difference that this equivalency is telling us. We're always taking the moment of the momentum with respect to G. This is the r prime, r sub I prime. But it's the difference is, are we using the momentum in the absolute frame, or are we using the momentum with respect to the mass center frame? So it's a really subtle difference, but using that we can say then from Newton's second law, the moment of Newton's second law, the sum of all moments acting on our system of particles equals the time rate of change of the angular momentum. Or we can say it's equal to the time rate of change of the angular momentum taken with respect to the mass center frame. It's a subtle difference. It's which momentum are you using when you calculate angular momentum? Absolute momentum or momentum with respect to the mass center frame? And whether you choose this one or this one all depends on what information you would have at hand. Do you know velocities with respect to the absolute frame or with respect to this moving frame attached to the mass center? You have a choice. You can use either one. So now we have equations of motion for a system of particles. We have the total external force acting on the system is equal to the total mass times acceleration of all particles in the system. We also have the sum of all moments on the system equals the sum of all moments of mass times acceleration. And note that we've also written this as L dot, where this is the L is the momentum of the system, or this one is the angular momentum of the system, time rate of change. Okay? Now, if the total external force is 0, we know that momentum is conserved. So if the total external force is 0, that means L dot is equal to 0, or L, the momentum, is a constant. So we can say momentum is conserved. We also can say now that if the total moment is 0, that means the time rate of change of angular momentum is equal to 0, which means that angular momentum is equal to a constant, or angular momentum is conserved. Okay? The important thing about this, we've used this fact many times looking for situations or even components where momentum is conserved. We can do the same with angular momentum. And one thing even more important is we get to choose the reference frame about which we take the moments. So, the origin about which we take these moments, we get to choose that. Which means if we can identify a point about which we take moments, that the moment is 0, then we will have a situation where momentum is conserved, angular momentum is conserved. So go looking for a coordinate origin, an origin about which to take moments that will give you a net moment of 0. If you can find that place, then you will be able to say angular momentum is conserved, and you'll have a simplified equation for determining kinetic relationships. We can continue to take advantage of this concept of mass center in a system of particles by expressing the kinetic energy using the mass center. So the kinetic energy for the system is just the sum over the individual kinetic energies of all the particles. Like that. Now we can express this in terms of the mass center as follows. We can write it as 1/2 mv hat squared. V hat now is the velocity of that mass center plus the linear momentum of every particle with respect to the origin attached to the mass center. So this is just, these two are equivalent, they're equal. This is just another way of expressing it in a convenient way that we'll use in systems of particles, and we'll also use this when we describe kinetic energy of rigid bodies. So we can use this concept of kinetic energy for a system to write the principle of work and energy for an entire system. The statement looks the same. We can just write it like that. That's a statement of the principle of work and energy for a system of particles, but we have to recognize that each of these quantities are the total for the system. So T now is total kinetic energy for the system, one of these two expressions that we've written above, and U is the total work acting on all particles in the system. And it's important to note you have to include internal forces in this work statement, because the work of internal forces don't necessarily cancel each other out. You have to be careful to identify those situations in which they do and do not cancel out before you can say that the work of internal forces cancel. So you just have to be careful about that. Now, if all the forces are conservative, we can turn our principle of work and energy into a statement of conservation of energy, which looks like that. Again, T is for the total kinetic energy of the system. V is the total potential for all particles in the system. Finally, we can also write a principle of impulse and momentum for a system of particles. Just like that, but recognizing now that L is the total system linear momentum, and the summation in front of the impulse integral simply highlights the fact that we're summing over all particles in the system. So we have to take the impulse of all of the external forces acting on each particle. There's one more equation, though. In the case of systems of particles, we can write a similar impulse and momentum equation for the moment impulse and angular momentum. So the total angular momentum of the system initially plus the sum of all moment impulses acting on the system equals the final angular momentum of the system. So those two equations represent the principle of impulse and momentum for a system of particles. And again, in this case, H is the total for the system.